So there's a Synopsys guy. Don't they have processor IP? That's the processor guy. Gee, I wonder what this talk is about. So not to disappoint, of course, I'll start this off. This will be the one slide. As many of you know, things are changing in the processor marketplace, especially a lot of things. People are getting very tired of ARM licensing fees and royalties and things like that, looking for options. There's certainly an option here. I encourage you to look at it. This is not what we're here to talk about, however. What we're really talking about is to talk about something different. And it's really talking about processors where, yes, there's a lot of different processor IP available on the market. You can go and you can check it out. You can find out, what clock, how many pipeline stages does it have? What is its clock frequency? What are its core marks? All these different kinds of things. This might be okay, but a lot of times you're looking for something that's a little bit different than that, or enhanced in some way. And that's really what we're interested in this talk today, is to talk about this, where basically if you look at this typical chart of application flexibility or generality in a processor architecture on one axis, and power and performance efficiency on the other axis, you can really see that there's a spectrum of different opportunities, all the way down to what you might call hardware accelerators or hardwired implementations. For us, the region of interest is in here, where you're trying to get something that you can't really get in a processor IP. And in any given SoC, there's some kind of functionality that just, if you ran it as software on the processor IP, you're going to have a non-competing product in the marketplace. It's not going to deliver the performance, or if it did, it'll melt one of the icebergs from one of the previous presentations. So we're looking at that. And in particular, we're going to talk about application-specific processors, or ASIPs, where basically the idea is that in order to achieve this performance, power efficiency, while still retaining programmability, you create a purpose-built processor implementation with an application-optimized ISA. Examples of these, I thought this was a good example since we're at Google today. The TPU, is a type of thing that's like this, or at least as far as we know from the information that has been brought out, is specifically tailored to application-specific workloads in the deep learning space. If you're in the deep learning space, you know that this is hot stuff. If you're not in the deep learning space, there's a lot of people talking about deep learning when they're talking about processor advancements. Deep learning just simply doesn't really fit on existing architectures, and this is definitely an area where there's a lot of architectural innovation happening. Just looking more, this is from AnandTech, some more articles about this. They imagine, I don't know if this is true or not, but they talk about straying away from standard data types. Maybe it's like a VLI DSP with SIMD with some twist. And this is what's interesting, right? So this is what we see in the application-specific processor space, is different variations of architectures that have VLIW, SIMD, and some twist. Specifically, if you look at that application domain, you can see there's a lot of different architectural options. They tend to break down into two categories. One category is parallelism, where you have instruction level parallelism, data level parallelism, multi-threading, multi-core, and so forth. Different types like that. And then all kinds of specialization. These can come from the simple cases for application-specific instructions, or even application-specific data types, like creating processor architectures whose native data type may be packets or complex numbers, or fixed point data types or something like that, that's native in the architecture, much like you would do if you were going to do a hardware implementation, to pipeline and connectivity and various different things that are specialized. So this is maybe a good example to put a circle around and call that some twist. So what I'm talking about here is that not only ASIPs, but in fact, Synopsys has a tool, it's called ASIP Designer, and it's a tool that can be used to automate the process of ASIP design. And the way that it works is that you basically describe a processor model. This is a high-level model written in a modeling language that is specifically created to capture instruction set architectures. You capture the instruction set architecture in that processor model, and the first part of the tool chain has this entire SDK with an optimizing C compiler, assembler, linker, instruction set simulator, interactive debugger, and profiler. That's automatically made available as a result of the processor model. Some important things to note is that the C compiler actually has an LLVM front end, so you have all the benefits of LLVM with respect to language extensions and other layers in the stack on top of that. Another thing to note is that this C compiler is what you call retargetable. So it's not a C compiler generator per se, it's actually a retargetable C compiler. What that means is every single one of our customers gets the exact same C compiler. So we're not in the business of creating a different C compiler for you that we have to spend time to manage, maintain, support, and so forth, and another one for somebody else. You know, the economies of scale don't work really well that way. Instead, it's a single compiler, and we support that single compiler for everybody. It's personalized by the processor model. You can take, there's a design process which is indicated by this 1 and 2 loop. The first step is that you actually create the SDK from the processor model. You can run your algorithms on there. That's where you're going to pick algorithms of interest. This is something that you want to accelerate or something like that. And you can opt, or you call it the benchmark set, but usually this is an application-specific benchmark set. You can run that on the tools. You can get information about it by running the instruction set simulator, which is a cycle-accurate simulator, and use a debugger and profiler to find out information about what's going on in that simulator, and use that information to incrementally refine the architecture. And in that way, you've got an iterative loop to incrementally optimize the architecture towards the benchmark set. So that's from an architectural perspective. And the key thing here, which we're highlighting, of course, is that we provide a number of example models with the tools, and one of the things we have is a RISC-V example model. It's a Zscale implementation, and I'm going to talk about an example of using it later. The other part is, once you get to a point where you feel like you have a good architecture from a performance perspective, you can also automatically generate the RTL and use your RTL tools to look at various things like area, operating frequency, power, and so forth. As you find issues in the RTL simulation, you can take that information and also incrementally refine the processor architecture and the processor model. The advantage of doing that is that you automatically keep the entire SDK up to date. So it's a single source. So if you go around and you ask the different people that talked earlier today and others that will talk later that are talking about hardware implementations, ask them, how did you create your RTL? How did you create your ISS? How did you create your C compiler? Chances are they leverage something like QEMU or something like that. So they have a nice starting point, but at the end of the day, those are individual projects that have to be developed by individual people that have to be cross-verified between themselves. So this is a single, kind of a single model type of approach that takes that away by keeping everything in sync. As I said, we have all kinds of different starting point examples showing lots of different kinds of things. The RISC-V model is in here. There's vector architectures with SIMD characteristics, DSPs, VLIW, and a bunch of interesting kind of domain-specific, which more than anything is probably something to give you some inspiration about the type of thing that you might be able to do. And these are all available with the toolchain. Just a quick note, this product has been in production for a long time. This is a list of publicly acknowledged customers that have used the tools. Basically, this is shipping today in hundreds of products worldwide. So that's a little bit about the tool. Let's talk about a methodology example. And we picked an example out of network processing. It's called robust header compression. You might be familiar with it. Or if not, this is really just presented as an example so you can see what the design flow is. And we're going to use the RISC-V example model as a starting point. Just to give a little overview of what the algorithm looks like. I mean, this is not surprising for anybody in networking. You go through a process where you do a compression and encoding, then you could do communication, and then you decompress on the other side. This is the type of thing where the data rates are very high and acceleration is appropriate to do. And you can look at different kinds of blocks in the algorithm. Here we highlighted some yellow blocks and some blue blocks. There's different aspects of that that could be accelerated. An alternative here, by the way, may, these might be algorithms running on a processor, or these might have been implemented in hardware as well, but maybe there's some use for flexibility to support different standards or different operating modes or things like that. There's different encoding methods, different things like that. We're going to talk, those are some examples of what could be accelerated in this case. We're going to mostly focus on, in the header field encoder, the WLSB algorithm, window-based least significant bit algorithm. We'll talk about that and how to accelerate that. And we'll use some of those same techniques to look at header parser acceleration as well, where the idea is that header parser is a little more control-oriented, and the WLSB is a little more data plane-oriented. So the general approach, we'll run select algorithms on the baseline model. We're going to identify issues, constraining performance, devise some enhancements, implement those enhancements, measure those, repeat as we try to improve the performance. And in the process, we'll consider parallelism, like VLIW and SIMD approaches. In this presentation, we're not going to cover SIMD, but SIMD is one of the capabilities of the tool chain, and also some twist, and in this case, application-specific instructions. So just to get started, talking about the RISC-V example model, this just summarizes what we've implemented. It's basically a Z-scale implementation. It's a three-stage implementation, single issue. It has a selectable either 16 or 32 registers. In this presentation, I think we've used only 32, the 32 register version of it. It's got a hardware multiplier. It's got a multi-cycle functional unit for division, so forth, emulation of IEEE floating point operations, and so forth. So this is what's available, basically out of the box. And that's what we started with. Just to give you some idea of how it performs, and this isn't to try to beat our chest and say we've got the best thing in the world or anything like this. All I'm trying to do is just set a baseline, because we're going to improve this and create an application-specific processor. This is just to say before we did any of that is what we had good. And good relates to the implementation, it relates to the compiler, and so forth. So here's a few data points. We got, from a Drystone perspective, there's two different ways. LLVM does, if you combine the Drystone benchmark into a single file and run the benchmark using LLVM, LLVM will do inlining. And so if you combine it into a single file, which isn't probably official on the benchmark, you get a higher number. It was unclear with some of the previous benchmarks whether they had done that or not. We presented both of the numbers. The top line with 1.25 is keeping it into the individual files the way that it comes off the benchmark. The 1.62 is simply a file concatenation, so they're in the same file. This UC Berkeley GCC one, this was from Yunsup's presentation from about a year ago, I think, or something like that. So that's from a Drystone perspective, and the point there is simply to say, looks reasonable, looks normal, like we're not somehow starting in the hole. On the implementation side, we basically did a synthesis of the TZ scale and then also the V scale benchmark off of GitHub. And we basically synthesized those under the same conditions using Design Compiler and came up with these cell areas. So TZ scale is a little bit smaller, but again, we're in the ballpark, right? And then also I thought it'd be useful to just look at, well, one of the algorithms. So we're going to look at the WLSB encoder algorithm. What does that look like? The ASIP Designer compiler versus the GCC compiler. We couldn't get our hands on a cycle accurate simulator for the RISC-V model. Maybe someone can let us know where to find that, but we didn't get that. But so what we did was we compared the number of instructions executed in running the benchmark, and you can see that those are fairly comparable. And for the purposes of looking at numbers later in the presentation, I included the number of cycles, the number of cycles per packet on the ASIP Designer space, because we're going to talk about cycle performance going forward in the presentation. So this is where these slides start to become eye charts. I apologize for this. I'm going to explain some of it. I'm going to go quickly through it. This is, if you want to look in more detail, we will be doing a demonstration over the Computer History Museum. Come find Drew or me, and we can go through and talk about these in more detail. But we'll just go through a couple iterations. One is, so first iteration, consider instruction level parallelism. We don't have a lot of reason to do that. The point of this is simply to show that it's easy to try. It's a common type of optimization for types of algorithms. It's easy to try. If you look at the algorithm here on the left-hand side, you can look at that and you can say, okay, well, there's some computation going. There's some loads and stores going. Maybe this will be useful. And by the way, the C compiler automatically knows about instruction level parallelism, and it will seek to find optimal schedules given the availability of instruction level parallelism in the architecture. So you simply, in the processor model, you simply say instruction level parallelism is possible, you compile a C algorithm that hasn't been changed. You didn't do anything to the C algorithm to create it. And it's a C compiler's job to find that parallelism that's available in the architecture. And this is a little, over on the right-hand side, this is a little bit of the NML model that describes that. And you can see here, there's an instruction 64. That's where we basically take the instructions that we had all before, which in the base model, there's ALU instructions, control instructions, div instructions, load store instructions. These things are already predefined. And so really all we did to create instruction level parallelism was we created a 64-bit instruction class at the base of this processor description. It's called instr64. And then in the next line, we identify instr64 as being an instruction in slot 0 and an instruction in slot 1. And then down here a little bit lower, you can see the operations for slot 0 and slot 1, which basically slot 0 is either an ALU instruction, a control instruction, a divide instruction, and slot 1 is a load store instruction. And so that's basically what we did. So we didn't really have to modify the model. This is working off of the existing RISC-V model, and we just created something from a single issue to a dual issue machine. Now, let's take a look at it. So if you look up here, and I'm not going to look at this too much because this is even more of an eye chart, but you can see on the top, in the top left, that's where the C code calls the loop that we were looking at, and over on the left you can see there's the assembly code, and you can see the appearance of 32-bit instructions and 64-bit instructions, and you can see that there's instruction level parallelism in the disassembly. So that's all fine and good. What were the results? Well, the results were here. So we're showing code size, cycle count, gate count. So we showed that the cycle count went from 1516 down to 1257, so decreased by 21%. And the gate count went up by 31%. It's really up to you. Is that good or not good? Maybe you were looking for a lot more performance. Of course, going to a 2-slot machine, the best you could do is half if you scheduled both slots every single time. But 21%, it's kind of up to you. Is that useful or not? And by the way, what is the cost? The cost is 31% increase in area. That's how it's an architect's tool. An architect's tool, it tells you what is the benefit, what is the cost, and allows you to make a decision about whether or not you're going to keep that kind of thing in the architecture or not. And what was the effort for this? It was a few lines of NML code and the pre-existing RISC-V model, and the ASIP designer tool. No changes to C code. So that's instruction level parallelism. Let's look at a second iteration. Let's consider some twist. And in this case, we'll just talk about an application-specific instruction, particularly for part of the robust header compression. And if you look at that, if you're looking down in the code, especially if you're a hardware designer, and you look at the C code and you can say something like, well, all that thing's really doing is a bunch of shifts and comparisons and different things like that. As a hardware designer, you're like, I can do that in a clock cycle. In C code, this is going to expand, to a whole bunch of instructions occurring serially because of the capabilities of the instruction set that you can find. But in hardware, you can look at that and say, I could do that in one cycle. Well, that sounds good. So the very first step, if you wanted to do that, instead of using that as C code, with ASIP Designer, what you do, the very first thing is you go create it. This is OPN. It's an operation. It's a definition of an instruction. So the first step is you want to add an instruction. So we'll add the acceleration instruction to the ISA. The RISC-V instruction set provides space in the opcode space to create these specialized instructions. So you create that with the image, and you identify what's going to happen in the first stage and the second stage and so forth. And you call, up in the upper right, you call this ROHC F32 primitive. And then down here in the box, that's the second step, where you basically describe what the primitive is. And there in that description, that part of the NML description is basically bit accurate C. And you can see that it's quite similar and in fact derived from the original C code. So you basically take a revised version of the C code that you wanted to accelerate, you put it into the behavioral description for the instruction, you create the instruction class, and you're good to go with the new instruction. Now, of course, you can't put anything in, if you put something in there that does, 500,000 multiply accumulates, you're not going to get that to run in a single instruction. So you have to be an architect. You have to be thinking about it. You have to know that this is a good idea. If this is a single cycle version. If you have something that takes multiple cycles, you can also create behavioral descriptions that are multiple cycles as well. So if we look at this, what you can see here, and this is just a proof point, and again, this is probably better shown in the demo, is that, here's the C code where we call it in the middle. This is just a repeat of the definition of the NML behavioral view. But the key point is over here in the bottom left, where in the machine code, you can see in the instruction sequence, you can actually see the instruction, the accelerated instruction that is identified there. And by the way, the compiler this whole time, so from a C code perspective, you're calling an intrinsic, but calling an intrinsic is exactly the same as calling a function. The C compiler takes advantage of knows that the instruction, has to figure out where to schedule it, and perhaps most importantly, has to figure out how to deal with register allocation and so forth. But that's something that compilers do, and you don't have to worry about it. So you don't have to get down to the assembly level just because you want to do something special. If we look at the numbers here again, so we can look at code size, cycle count, gate count. So basically compared to the baseline, so for this slide, we took the instruction level parallelism out that we did previously. So this is compared to the baseline. We went from 1,500 cycle count down to 500, so a 67% improvement in performance. With a few more lines of NML code. I showed you what those NML code changes were. And we changed the C code because we had to call the intrinsic instead of the C function. Or we could have named our intrinsic the same thing and done a linking trick. So that's that for putting the application-specific instruction in there. You might ask, well, what happens if I do both? I happen to have that number. So this is with the instruction level parallelism and the custom instruction for this WLSB algorithm. So overall, that's a 73% improvement from 1,500 down to 400. And you can see the area changes. Perhaps one thing that's interesting is that custom instruction, you can see, is only 9% more on the area. So you might look at this and say, because you were able to explore this and see what these options are, you might come to the conclusion like, well, the custom instruction is really good and really worth it because it doesn't cost very much. And gee, that instruction level parallelism costs a lot, and maybe I'd rather forego that or not. It gives you the opportunity to make that architectural decision. So then just looking at one more iteration. So the third iteration, looking at the header parser code, and I'm not going into this one in as much detail, but in the top left, on the underline there, what you can see there is there's a conditional expression where you're comparing a variable to a small constant. And if you look at the code, you may look at that and say, gosh, in my code, that happens a lot. And in the regular RISC-V instruction set architecture, it would, in order to execute that, because as register to register compare and jump, you have to load the register with the immediate, and then you do the compare and jump. So maybe I get a benefit just by creating an instruction that actually does a comparison against a small immediate. And I have enough space in the opcode space to do that as well. So we created that instruction here, and with the NML description down on the bottom, and then you can see the branch if not equal with an immediate in the second position there on the right. So that's an example. Again, looking at performance. So looking at code size, cycle count, the gate count. This was a negligible, as you might guess, this was negligible on the gate count percentage. Cycle count, for this algorithm, the header processing algorithm went from 289 to 242. That's a 16% performance improvement. 16%, not too bad for a small bit of work for a piece of control code. And this is just to describe different kinds of ideas that you can do. So we did a few more lines of NML code, reran the benchmark, no changes to the C code. So takeaways. So hopefully through this process and talking about these different examples, I've pointed out, ASIPs are interesting. They're interesting for a piece where you're trying to do acceleration in particular, heavily used in different application domains, imaging, vision applications, wireless applications, different things like that, especially where something where you want to do something, you want to have an accelerated result, and you don't have, the processor IP that's out there doesn't serve those kinds of needs. This is a great use for ASIPs. ASIP Designer as a tool automates this process from a single source, so keeping everything in sync. It's an important aspect. We've got a RISC-V model, which is perhaps the big news. As a result of this, we hadn't talked about that publicly previously. And really that the thing about it is that you can evaluate these options very swiftly. So I think that's it. Thank you.
Number 3, please. There we go.
Hello, Yonsat Lee from Sci5.
Hello.
Now that you implemented RISC-V, how does RISC-V compare to ARC? What's your opinion on that?
So, I mean, I think there's lots of different architectures out there. I mean, we're clearly in the business of ARC. We have a lot of optimized implementations around these things. We've got, licensees. We've got a lot of licensees. We're number 2, in the market with respect to processor IP against another company that starts with an A and an R. I mean, it's an important business for us. I think that there's a lot of things about it. It's outside the scope of my talk, but when you do processor implementations, I think you guys at Sci5 are doing the same thing. You're picking particular items. What I expect to see from you, I'd be interested to see, is that you're going to optimize for particular uses because you see that there's a market opportunity. We've done the same thing. So.
Go ahead.
Okay. Steve Wallach, Micron. How does your tool chain deal with if I have a different machine state that I add register sets, or if I reference memory in a way that's not supported, currently supported?
I'm not sure how you could reference memory in a way that's not currently supported, but that just may be because I'm not stretching my brain enough.
Stretch.
On that. I mean, so we support the ability to do. We support multiple memories, and you can do memory interfaces in your own way.
You may want to add an atomic operation to memory, for example. That's not supported.
Do you have, Drew, would you like to take that question?
Yeah, because the processor model is language based, you can describe anything. So that kind of a function you can describe pretty easily. And it's not something that is part of the base instruction set of or availability of RISC-V, but it's something you could easily describe as part of the whole process.
Okay, and what if I want to add, I don't know, 16 more registers of various entities?
Yeah.
Is that dealt with in a straightforward manner?
Yeah.
Yeah, you describe the registers. It's just part of. I mean, I didn't cover this too much, but it's a language-based approach. So it's not. A lot of people ask, like, so what is your template, and what are the boundaries of the template, and what can't I do? And that's not really the way the tool works, because it's a language-based approach. If you don't have a program counter, then it's probably not the right tool for you. But if you have a program counter and you're fetching instructions and so forth, the rest of the tool allows you to describe the architecture that's there. So it'll have data paths, it'll have registers. So for example, there's lots of examples of designs where there's registers of different different data types for different registers. The registers may be distributed. So processors in general have sort of circular natures where there's a central register file. I mean, the RISC-V architecture is one of them, where there's a central register file and you're taking operands and executing on them and restoring them back. But that's not a necessity with this tool. You can have distributed register architectures, and the compiler will understand what the data paths that are available to get, because it knows how it needs to schedule operations, and it needs to figure out how to get the data from where it was, where the last computations were to the new computation, and it will understand that how it gets there through the architecture that you define.
Thank you.
So 2 questions, one business, one technical. Have you compared the efficiency of the automated implementation from NML to some of the standard open source deliverables in terms of code compactness, how it implements? Because your RTL is automatically generated, right? That's one. And then 2, do you have any, given that RISC-V is open source, do you have any plans to open source the NML code for RISC-V, for example?
So on the NML, we don't have plans to open source the NML. We haven't talked about doing that. So that's not, we certainly don't have a plan. Is it something to think about? Sure, I think that's something to think about. With respect to comparisons, you were talking about RTL comparisons?
Yeah, so the output of a
The output of ASIP compiler versus your versus some of the standard deliverables. We had like,
Yeah.
I lost count how many
Yeah.
open source RTL versions are on GitHub and wherever.
Yeah. So, I mean, we presented the comparison against the vScale implementation to show, a similarity in the presentation. So that those numbers are in there. We're a little bit better. I didn't spend a lot of time saying, oh, wow, we're better. I mean, it looks like it's in range. I think, the main question is that a lot of people are like, well, it's an automation tool. It can't be good. You have to pay. Basically, you're going to pay inefficiency. And if you make that assumption, I'll just say you're making the wrong assumption. We'd be glad, if somebody's interested in using the tool, we'd be glad to go through a process and actually do benchmarks and show you some of those. And we have done benchmarks. That's the one we've done for RISC-V, but we've done benchmarks with other architectures for other processors where we compared what was created by the tool against the design team that had created the design using hand-built methods on RTL, and compared those and basically came up with a wash with respect to sizing. Yeah. Within a few percentage points.
We filled the presentation time with lots of good slides. So
Yeah.
we'll take one more question. We're running a little behind here.
Oh, so what's the engagement model if you were interested in this, and how much would it cost?
Yeah, it's a good question. I won't talk about prices specifically, but it'll be, the engagement model is a license. It's a software tool that you get a license for, and you can create whatever designs you want with it. So it's licensed in that fashion. So, and there's no royalties associated with it or any of that.
Okay. Thank you.
All right.
Thank you.
Steve.